Welcome to today's session. In this video, we will tackle LeetCode problem number 565, titled Array Nesting. This problem challenges us to find the largest set of indices we can traverse based on the values in the array. We'll explore its requirements and dive into solving it step by step. Let's get started. In this problem, you are given an integer array nums of length n. The array nums is a permutation of the numbers from 0 to n1, meaning it contains all integers in this range exactly once, but possibly in a shuffled order. Your task is to find the size of the largest set S that can be formed by following a specific process. The process starts with any index I in the array. From there, you repeatedly access the value at the current index to determine the next index. Specifically, if the current value is nums, s, k1, then the next value is determined by looking at the element at that index. You continue this process until you encounter a value that already exists in the set, forming a cycle. The goal is to return the size of the largest set you can create using this method. Let's look at some examples to understand this better. Imagine the input array nums is 5, 4, 0, 3, 1, 6, 2. Starting at index 0, the value at nums, 0, is 5. From there, you move to index 5, which gives you the value 6. Next, at index 6, the value is 2, and at index 2, the value is 0. At this point, you return to the starting value, which means a cycle is formed. The set created from these indices is 0, 5, 6, 2, and its size is 4. If you start at other indices, you'll find smaller sets. Therefore, the largest set size is 4. In another example, if nums is 0, 1, 2, 3, 4, each index simply points to itself, forming sets of size 1. The largest set size in this case is 1. Now, consider the input nums equals 1, 0, 3, 2. Starting at index 0, the value is 1, and at index 1, the value is 0. This forms the set 0, 1 with a size of 2. Similarly, starting at index 2, the value is 3, and at index 3, the value is 2, forming the set 2, 3, with a size of 2. Since both sets have the same size, the largest set size is 2. These examples illustrate how the process works and how the size of the largest set depends on the cycles formed within the array. To summarize, the problem has some key constraints and edge cases to consider. First, the array nums is guaranteed to have unique values, and each value lies within the range 0 to nums.length 1. For edge cases, if nums has only one element, the largest set size is 1 because it forms a trivial cycle. When each index points to itself, as in nums equals 0, 1, 2, 3, the largest set size is also 1. For arrays that form a single large cycle, such as nums equals 1, 2, 3, 0, the largest set size equals the length of the array. Finally, if the array contains multiple disjoint cycles, the size of the largest cycle determines the output. These constraints and edge cases help guide you in designing an efficient solution for the problem. To approach this problem, we first consider a brute force method to understand the underlying mechanics. The goal is to find the largest set of indices that can be visited starting from each index, based on the given traversal pattern. The intuition here is that we simulate the process of jumping from one index to another, following the values in the array, until a cycle is detected. To achieve this, we iterate over all indices, use a visited array to avoid counting the same element multiple times, and determine the size of the set formed by each traversal. A few important observations simplify the problem. Since this array represents a permutation of indices, each element is part of exactly one cycle, and the cycle length corresponds to the number of unique elements visited during a traversal. While this approach is straightforward, it has significant drawbacks. Its time complexity is n squared, since we could end up traversing an entire cycle for each index, even if the elements in that cycle have already been visited. Additionally, it uses n space for the visited array, making it less suitable for larger inputs. To address the inefficiencies of the brute force approach, we consider an optimized method. The key insight here is that once we identify a cycle, all elements within that cycle belong to the same set, so there's no need to revisit them in future iterations. This allows us to mark elements as visited during a single traversal and skip those elements entirely in subsequent iterations. An efficient way to do this is to use the input array itself as a marker, temporarily modifying values to indicate that an element has already been processed. For instance, we could set visited elements to a sentinel value like -1. In terms of implementation, we start by initializing a variable to keep track of the maximum set size. Then, we iterate through the array, and for any unvisited index, we traverse the cycle starting from that position, marking elements as visited along the way. The size of the cycle is counted during this traversal, and we update our maximum size if this cycle is the largest encountered so far. This optimized approach significantly improves the efficiency of our solution. The time complexity is reduced to O(n), as each element is visited exactly once during the entire process. This is a major improvement over the O(n²) complexity of the brute force method. Additionally, the space complexity is reduced to O(1), because we use the input array itself for marking visited elements, eliminating the need for an additional visited array. The advantages of this approach are clear. It is highly efficient for large arrays and avoids redundant work by marking cycles during traversal. However, there is a trade-off to consider. Modifying the input array in place may not be acceptable in scenarios where the integrity of the original array must be preserved. Nonetheless, for problems like this one where the input array does not need to remain intact, the optimized approach is the ideal choice. It balances efficiency with simplicity, making it well-suited to handle inputs of any size within the problem's constraints. The chosen strategy for solving this problem is the optimized approach, due to its linear time complexity and constant space usage. The main insight that drives this strategy is the realization that cycles can be marked during traversal, ensuring that no element within a cycle is processed more than once. This avoids redundant work and guarantees efficient handling of even the largest allowable inputs. While modifying the input array is a trade-off, it is acceptable in this context because the array is not required to remain unchanged after the computation. By leveraging these optimizations, we can ensure that the solution is both scalable and practical, making it the best choice for this problem. In this problem, we are tasked with finding the size of the largest set of indices in an array, where the traversal through the indices follows a specific pattern. Starting from any index I, we repeatedly jump to the index specified by nums I, then nums I, and so on, until we encounter an index that has already been visited, thus forming a cycle. Each index can only belong to one set, and our goal is to determine the size of the largest such set. To solve this, we use a systematic approach. First, we initialize a Boolean array called visited to keep track of whether a particular index has already been processed. This ensures that we don't revisit indices unnecessarily. Then, we iterate through each index in the array. If an index has already been visited, we skip it, as it has already been accounted for in a previous traversal. Otherwise, we begin a new traversal starting at that index to calculate the size of the cycle it belongs to. When starting a traversal, we initialize a local variable current to the starting index I and a counter size to 0, which will track the number of indices in the current cycle. As long as the current index hasn't been visited, we mark it as visited, increment the size counter, and then move to the next index in the sequence by updating current to nums current. This process continues until we encounter an index that has already been visited, signifying the end of the cycle. Once the cycle is complete, we compare the size of the current cycle with a global variable max_size, which stores the largest cycle size encountered so far. If the current cycle is larger, we update max_size. After processing all indices in the array, we return the value of max_size, which represents the size of the largest set. Now, let's focus on the underlying principles that make this algorithm both efficient and correct. First, the traversal inherently detects cycles in the array. By repeatedly following indices, we eventually encounter a repeated index, which guarantees that the traversal terminates. This cycle detection is key to solving the problem. Second, the visited array ensures that each index is processed only once. This eliminates redundant computations, as any index that has already been visited is skipped in subsequent iterations. When analyzing the time complexity, we observe that each index is visited at most once, resulting in a total time complexity of O(n) for an array of size n. The space complexity, dominated by the visited array, is also O(n), making the algorithm both time and space efficient. To efficiently implement the solution, we rely on two primary data structures. The visited array plays a crucial role in tracking whether each index has already been processed. This prevents redundant traversals and ensures that the algorithm runs efficiently. Without it, we might repeatedly process the same indices, leading to unnecessary computations. Additionally, we use counters to manage the logic of the algorithm. The size counter keeps track of the number of indices in the current cycle during a traversal, while the max_size counter stores the largest cycle size encountered so far. These counters simplify the process of comparing and updating the maximum set size, ensuring the algorithm remains straightforward and easy to implement. To better understand the algorithm, let's walk through an example with the input array nums equals 5, 4, 0, 3, 1, 6, 2. First, we initialize the visited array to false, 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 and set max_size to 0. Starting at index 0, we follow the cycle 0, 5, 6, 2, 0. During this traversal, we mark the indices 0, 5, 6, and 2 as visited, updating the visited array to true, false, true, false, false, true, true. The size of this cycle is 4, so we update max_size to 4. Next, we skip indices 2, 5, and 6, as they are already marked as visited, ensuring we don't process them again. Continuing from the remaining indices, we start a new traversal at index 1. This time, the cycle is 1, 4, 1. During this traversal, we mark indices 1 and 4 as visited, updating the visited array to true, 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 false, true, true, true. The size of this cycle is 2, which is smaller than the current max_size, so max_size remains 4. Finally, we skip indices 3, 4, 5, and 6, as they have already been visited. At the end of the process, the largest set size is determined to be 4, which we return as the result. This solution to LeetCode problem number 565 array nesting efficiently calculates the size of the largest set S that can be formed by traversing the given array nums. Let's break the code down. 1. Initialization. We calculate the length of the input array nums and store it in N. A visited list of the same length is initialized with false values to track whether each index has been processed. This ensures we avoid revisiting indices and redundant computations. The max_size variable is initialized to 0, which will store the size of the largest set encountered during the traversal. 2. Main loop. We iterate through each index I of the array. If an index has already been visited, it means it is part of a set that has already been processed, so we skip it. If the index is unvisited, we begin a new traversal to calculate the size of the set starting from that index. 3. Traversal of the set. Starting from the current index I, we initialize current_size to 0 and set current to I. We then repeatedly follow the sequence current equals nums, current, until we revisit an already visited index. Each time we visit a new index, we mark it as visited in the visited list and increment current_size. 4. Update maximum size. After completing a traversal, we compare current_size with max_size and update max_size if the current set is larger. 5. Result. Once all indices have been processed, the max_size variable holds the size of the largest set, which is returned as the result. ### complexity analysis. Time complexity, O(n), since each index is visited at most once. Space complexity, O(n), due to the visited array. This approach is efficient and avoids redundant computations by marking indices as visited on the first traversal itself. It guarantees that each element is processed exactly once, ensuring optimal performance even for larger inputs. This is the Java implementation of the array nesting problem, following the exact logic in the Python solution. The algorithm uses an array to track visited indices and iterates through the input array, computing the size of each set formed by the array's nesting structure. Key differences include explicit type declarations for variables, the use of Java's Boolean for visited tracking, and Java-specific syntax and conventions in the class structure. To solve the array nesting problem, we start with the input array nums equals 5, 4, 0, 3, 1, 6, 2. We initialize a visited array to keep track of which indices have been processed, and set max_size to 0, which will store the size of the largest nesting we find. The outer loop begins with I equals 0. Since visited, 0, is false, we enter the inner loop. Here, current underscore size is initialized to 0, and we set current to the value of I, which is also 0. Inside the inner loop, we mark visited, 0, as true, move to the value at nums, 0, which is 5, and increment current underscore size to 1. Repeating this process, we mark visited, 5, as true, move to nums, 5, equals 6, and increment current underscore size to 2. Continuing, we mark visited, 6, as true, move to nums, 6, equals 2, and increment current underscore size to 3. Finally, we mark visited, 2, as true, move to nums, 2, equals 0, and increment current underscore size to 4. At this point, current is back to 0, which is already visited, so we exit the inner loop. The size of this nesting is 4, so we update max underscore size to the maximum of its current value in 4, resulting in max underscore size equals 4. Next, when I equals 1, visited, 1, is false, so we process this index. Inside the inner loop, we mark visited, 1, as true, move to nums, 1, equals 4, and increment current underscore size to 1. Then, we mark visited, 4, as true, move to nums, 4, equals 1, and increment current underscore size to 2. At this point, current is back to 1, so we exit this nesting loop. The size of this nesting is 2, but since max underscore size is already 4, it remains unchanged. Finally, for indices I equals 2 to I equals 6, all of them are already visited, so we skip them, leaving max underscore size unchanged at 4. For this example, we conclude by returning the max underscore size value, which is 4. Now, let's look at another example with nums equals 0, 1, 2, 3. We initialize visited as false, 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 and set max underscore size to 0. Starting the outer loop with I equals 0, we see visited, 0, is false, so we enter the inner loop. Here, current underscore size begins at 0, and current is set to 0. Inside the inner loop, we mark visited, 0, as true, move to nums, 0, equals 0, and increment current underscore size to 1. Since current is back to 0, which is already visited, we exit the inner loop. The size of this nesting is 1, so we update max underscore size to max, 0, 1, equals 1. For indices I equals 1 to I equals 3, each follows the same pattern. We process the index, mark it as visited, and find that it forms its own set of size 1. Since all indices loop back to themselves, max underscore size remains 1. After processing all indices, we return max underscore size equals 1 as the final result for this example. In this final example, we use nums equals 1, 0. The visited array is initialized as false, false, and max underscore size starts at 0. For I equals 0, visited, 0, is false, so we enter the inner loop. Here, current underscore size begins at 0, and current is set to 0. Inside the loop, we mark visited, 0, as true, move to nums, 0, equals 1, and increment current underscore size to 1. Then, we mark visited, 1, as true, move to nums, 1, equals 0, and increment current underscore size to 2. At this point, current is back to 0, which is already visited, so we exit the inner loop. The size of this nesting is 2, so we update max underscore size to max, 0, 2, equals 2. For I equals 1, visited, 1, is true, so we skip this index. With all indices processed, we return max underscore size equals 2 as the result for this example. The time complexity of this solution is O(n). Let's break this down step by step. First, we have the outer for loop, which iterates over all the indices of the array. If the array has n elements, the loop could potentially run n times. However, we skip indices that have already been visited, so not all iterations trigger the inner while loop. Next, the while loop is responsible for traversing cycles within the array. The key here is that each index is visited exactly once during the entire process. This is because once an index is marked as visited, it cannot be revisited. As a result, the total number of times the while loop executes across all cycles is at most n. To formalize this, every index contributes a constant amount of work, like marking itself as visited or accessing its value in the array. Since there are n indices, the total work scales linearly with the size of the array, resulting in an overall time complexity of O(n). Now let's examine the space complexity, which is O(n). The primary reason for this is the visited array, which has the same length as the input array nums. This array is used to track which indices have already been processed, and it requires O(n) additional space. Apart from the visited array, the algorithm only uses a few extra variables like max_size, current_size, and current. These variables are independent of the input size and require a constant amount of space, or O(1). When we combine these factors, the total space complexity is dominated by the visited array, leading to an overall space complexity of O(n). Let's compare this solution to a brute force approach. A naive method might involve generating all possible subsets or cycles within the array and then determining their sizes. Such an approach would have a time complexity of O(n², in the worst case because it could involve redundant checks for cycles or subsets. Additionally, the brute force approach might still require O(n) space to track visited elements or store intermediate results. In contrast, the optimized solution avoids redundant work by ensuring that each index is visited exactly once. This reduces the time complexity to O(n), while the space complexity remains O(n) due to the visited array. This makes the optimized approach both faster and more efficient in handling larger inputs. To further analyze the performance, let's consider best, average, and worst case scenarios. In the best case, the nums array forms a single cycle that includes all n indices. Even in this case, the algorithm must visit every index, so the time complexity remains O(n). On average, the array will contain multiple cycles of varying lengths, but since each index is still visited exactly once, the time complexity continues to be O(n). In the worst case, the array either forms one large cycle or has cycles distributed such that every index must still be checked, which also results in O(n) time. In summary, the solution consistently achieves O(n) time complexity and O(n) space complexity across all scenarios. This efficiency makes it significantly better than a brute force approach while keeping memory usage minimal. When tackling the array nesting problem, there are some common mistakes to avoid. First, many beginners overlook how cycles work in the traversal. If you don't check whether an index has already been visited, you could end up in infinite loops or get incorrect results. To prevent this, always track visited indices with a visited array or a set. Another pitfall is misunderstanding the problem's constraints. For instance, the input array always contains integers from 0 to n1, just shuffled. If you miss this, you might spend time handling unnecessary edge cases or overcomplicate your solution. Additionally, avoid overusing nested loops. A naive solution might simulate every sequence from each starting index, which can lead to an inefficient O(n² time complexity. Instead, focus on optimizing your approach. Lastly, watch out for mistakes with the visited array. Some solutions reset it after every starting index, which is wasteful. Instead, mark all elements in the current cycle as visited and skip them in future iterations for better efficiency. Edge cases are another area where mistakes frequently occur. For example, consider arrays with just one element, arrays where all elements are the same, or cases where every element forms a self-loop. If you don't account for these scenarios, you risk runtime errors or incorrect outputs. Now, let's think about this problem in the context of interviews. A key takeaway is that it's a test of your ability to identify and manage cycles within an array. Conceptually, it's similar to a graph traversal problem where each index points to another. During an interview, it's important to demonstrate your understanding of the inefficiencies in brute force approaches and quickly pivot to an optimized solution using a visited array or in-place marking. Be ready to explain the trade-offs between extra space, like a visited set, and modifying the input array directly. Finally, as you solve the problem iteratively, make sure you clearly articulate how you avoid revisiting indices and how you detect cycles effectively. This problem is closely related to several other problems, making it a great opportunity to showcase your ability to draw parallels. For instance, LeetCode 287, which involves finding a duplicate number, uses cycle detection techniques like Floyd's tortoise and hare algorithm. Similarly, LeetCode 142 focuses on detecting the start of a cycle in a linked list. Of course, there's LeetCode 565 itself, which centers on finding the largest set of indices without revisits. A slightly different problem, LeetCode 41, involves finding the first missing positive number, but it also relies on in-place manipulation of arrays and achieving O1 space complexity. In terms of approaches, brute force is the most straightforward but also the least efficient. Simulating traversals from every index results in n² time complexity, which is impractical for larger inputs. While this method is easy to implement, it's not ideal and should only be mentioned to highlight its inefficiencies. More efficient approaches include using a visited array, which ensures each index is processed only once. This reduces the time complexity to n, while requiring n extra space. It's straightforward to implement and is often a preferred solution in interviews. Alternatively, you can use in-place marking, where the nums array itself is modified to track visited indices. This eliminates the need for extra space, achieving O1 space complexity alongside n time. However, modifying the input array might not always be allowed in interviews, so be sure to ask the interviewer if this is acceptable. Lastly, there's Floyd's tortoise and hare algorithm, a more advanced technique that treats the problem as cycle detection in a linked list. This approach is elegant and achieves n time in O1 space, but it requires a deeper understanding of cycle detection and might be harder to explain under time pressure. Choosing the right approach depends on the constraints and the interviewer's expectations. Great job on completing the problem. To summarize, we explored strategies to solve array nesting and highlighted the importance of efficient traversal techniques. Remember to practice similar problems to improve your problem-solving skills. Thanks for watching, and don't forget to like and subscribe for more coding tips. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!